Okay, in this lecture we're going to finish our section 6.3 material on step functions. And we've seen that step functions have some nice applications when we're working with piecewise functions. So now we're going to consider taking the Laplace transform of a unit step function, or the Laplace transform of a unit step function times some function of t. And we'll see that the Laplace transform of these step functions have some very nice properties. So let's start with the following example. We are asked to find the Laplace transform of the unit step function u sub c of t for c greater than or equal to 0. So let's take a look at it. If we have the Laplace transform of this unit step function, by definition, this is the integral from 0 to infinity of e to the negative st times my unit step function, u sub c of t. And this unit function, let's recall how it's defined. It is a piecewise defined function, which is 0 for all t less than c, and 1 for values of t greater than or equal to c. So since this function is defined differently over different t intervals, to evaluate this integral, I could split the integral into the sum of two integrals. The first from 0 to c, where we would have e to the negative st times, well, for values of t less than c, my unit function is 0. And then I would add the integral from c to infinity of e to the negative st times, for values of t greater than or equal to c. The value of our function is 1 dt. So this first integral gives us a value of 0, and we're left with the integral from c to infinity of e to the negative st dt. And to evaluate this, we need to make use of a limit. We could take the limit, say, as n approaches infinity, of the integral from c to n, e to the negative st dt. And so this gives us the limit as n approaches infinity of negative 1 over s e to the negative st, evaluated from c to n. So we have the limit as n approaches infinity of negative 1 over s e to the negative sn minus a negative 1 over s, gives me plus 1 over s, e to the negative c times s. And now, as n becomes large, this exponential term, e to the negative sn, will decay to 0, provided that s is positive. So I'm left with 1 over s times e to the negative cs for s greater than 0. So here we have found the Laplace transform of a unit step function, and this transform is summarized in our table of Laplace transforms as property number 12 here. The transform of u sub c of t is e to the negative cs over s for values of s which are positive. So let's look at an example making use of this new result. In this next example, we are asked to sketch the graph of f of t, which is u1 minus 2u4, and find its Laplace transform. So let's start with sketching the graph of this function. When I look at this function, I see it's defined in terms of unit functions at time 1 and time 4. So I know that jumps occur, or changes in definition occur, at time 1 and 4, which means that I can think about my function as being defined over the intervals from time 0 to 1, from 1 up to 4, or for values of t greater than or equal to 4. And let's look at how it's defined on each of these subintervals. So for time 0 to 1, both of these unit functions have not yet turned on. They're both valued as 0. So I have 0 minus 2 times 0 is 0. On the interval from 1 to 4, my first unit function has turned on to a value of 1. The second one is still valued as 0. So I have 1 minus 2 times 0. And then for values of t greater than or equal to 4, both of my unit functions have turned on to a value of 1. And so my function f would be 1 minus 2 times 1, which leaves me with negative 1. So my graph of this function in the ty plane, well, it's defined as 0 from time 0 until time 1, where the value of our function then jumps to y equals 1. And then it's defined as a constant 1 until we hit time 4, at which point the value becomes negative 1. And is then defined as negative 1 for all time greater than or equal to 4. So we have our graph, and now we're asked to find the Laplace transform of this function. So here, the Laplace transform of f of t. Well, it's written in terms of the unit step function. And since the transform is linear, I can take the transform term by term for this function. And so using the new result that we just found, the Laplace transform of u1 is e to the negative 1s over s. And then I have minus 2 times the transform of u4, which would be e to the negative 4s over s, provided that s is positive. So we see here that we can find the Laplace transform of a piecewise defined function, f of t, by rewriting it in terms of a unit step function, and then taking the transform of those step function terms. Now, another function that we will often consider throughout Chapter 6 is a unit function multiplied by some function of t. So let's consider the following. Suppose that we have a given function f, which is defined for non-negative values of t. Then we will often consider a related function, g, which is defined as follows. G of t is the product of my unit step function u sub c times the function f of t minus c. Or if we write out the piecewise definition of this function, for values of t less than c, we have 0, and for t greater than or equal to c, I have 1 times f of t minus c, or just f of t minus c. So this function g represents the translation of the function f, a distance of c units in the positive t direction. So let's see how to interpret this g of t function. So if I have a given function, y is f of t, and it's defined for t greater than or equal to 0. So let's say at time 0, the value of my function is f of 0. And let's say the graph of this function is some nice smooth curve in the ty plane. Then let's look at the graph of this g of t function. In our ty plane, I'm going to consider y, which was u sub c times f of t minus c. And so this function is defined as 0, starting at time 0, until we reach time c, at which point y would be 1 times f of c minus c, so that would be f of 0, and then f of t minus c, well, we would have the same graph that we had for f of t, just shifted c units to the right. So this product of my unit step function times f of t minus c corresponds to translating the function f c units in the positive t direction. Or we can think about this product as sort of turning on the function f of t at the time c. So for this type of function, we will be interested in the Laplace transform. So our following result, this is theorem 631 from your text, says if the Laplace transform of a function little f of t, let's call it capital F of s, exists for some values of s, and if c is a positive constant, then the Laplace transform of the unit step function times f of t minus c is equal to e to the negative cs times the Laplace transform of the function f that was being translated, c units to the right. Or we could write that as e to the negative cs times the Laplace transform of f. Or if we think about this theorem in terms of an inverse transform, so conversely, we could say if little f of t is the inverse transform of a function capital F of s, then the inverse transform of e to the negative cs times that f of s function would be the unit step function at time c times the inverse transform of capital F, which is little f, but translated c units to the right, or c units in the positive t direction. Now this theorem is one of our more frequently used results as we're going to move forward throughout chapter 6. So let's take a look at the proof of this result. I'm looking for the Laplace transform of the unit function times f of t minus c, which by definition is the integral from 0 to infinity of e to the negative st times the function I'm taking the transform of, integrating in terms of t. And as with our previous example, since this unit function is defined as either 0 or 1, well, on the interval from 0 to c, I have nothing, and then I would add the integral from c to infinity of e to the negative st times 1 f of t minus c dt. So now let's take a look at what we have. We're trying to integrate this function, and I see that part of my integrand involves a composite function. So to integrate these composite functions, usually we'll try a substitution. Now I've already used u as the notation for my unit function, so let me make a substitution of w is equal to t minus c, the interior function in that composition. In which case dw would be 1 dt. And now let's rewrite this integral in terms of w. So let me start by changing my limits of integration from t values to w values. So for the lower limit, if t is equal to c, then w would be c minus c, or 0. And for the upper limit, as t becomes infinitely large, w, which is t minus c, would also become infinitely large. And I then have e to the negative s times t. So solving for t in terms of w, I have w plus c times f of what we call w. And then on the end, dt is just the same as dw. So for this exponential term that I have out in front, e to the negative s times w plus c, I can think of that as e to the negative cs times e to the negative sw. And since e to the negative cs does not depend on w, I can bring it out in front of my integral, leaving me with the following. And so I now have e to the negative cs times, let's take a look at this. This integral on the end is from 0 to infinity, e to the negative sw times f of w dw. And this is the exact definition of the Laplace transform of the function f. I'm just replacing the variable t by w, but it gives me the same result. And this is what I wanted to establish. So as a note here, what does this theorem say? Well, this theorem 6.3.1 states that the translation of a function f of t, a distance of c units in the positive t direction, corresponds to multiplication of the Laplace transform of that function by the exponential e to the negative cs. And this result, theorem 6.3.1, is summarized in our Laplace table as property number 13. The transform of a unit function times f of t minus c is e to the negative cs times the Laplace transform of the function that was being translated. So now that we have this result, let's look at some examples making use of this. Here we are asked to find the Laplace transform of this function, f of t, which is defined piecewise as 0 for t less than 1, and t squared minus 2t plus 2 for t greater than or equal to 1. So here, when I see that this is a piecewise defined function, and I'm trying to find my transform, let me see if I can express this in terms of the unit step function, now that I know how to find the Laplace transform of the unit step function. So let me say here, our function f of t, well, it's defined as 0 until time 1, where a change in definition occurs. So I could take u1, and then I would multiply by the value that I want my function to take, which is t squared minus 2t plus 2, minus 0. So we have the following. I've got f of t is the unit function at time 1 times this quadratic. Now, to use this new result, theorem 631, well, I have to make sure that my function has the proper form to match that theorem, which means that whatever comes after my unit function, I have to think of as something that's been shifted c units, in this case 1 unit, to the right. So an easy way to do this here is to take that quadratic and complete the square, giving me t minus 1 squared plus 1. Or if I distribute that unit function, I have u1 times t minus 1 squared plus u1. So my Laplace transform, capital F of s, well, taking my transform of each piece, I'm looking for the transform of u1 times t minus 1 squared plus the transform of u1. So for this first piece, using my new theorem, 6.3.1, I have the product of a unit step function at time 1 and t minus 1 squared, which is just the function t squared shifted 1 unit to the right, or translated 1 unit in the positive t direction. So my new theorem says I would take the product of e to the negative 1s times the Laplace transform of the function which was being shifted, which was my t squared function. And then I'm still adding on the end the Laplace transform of u1. So using my table of transforms, I have e to the negative s times the transform of t squared, which would be 2 factorial, or 2, divided by s to the 2 plus 1, so s cubed, plus the transform of u1, which would be e to the negative 1s over s. Or if you prefer, we can factor out e to the negative s leaving us with 2 over s cubed plus 1 over s. So let's look at another example of this. In the next example, we're asked to find the Laplace transform of this function f of t, and we can see that it's defined in terms of the unit step function, u1 and u2. And I'm multiplying these functions, u1 and u2, by some function of t. So I'm going to be making use of my new theorem. And if I want to make use of this theorem, I need to rewrite my function f of t so that whatever comes after the unit step function, I can think of as a function which has been translated c units to the right. So for this first part, I had u1 times t minus 2 plus a u2 times t minus 1. Or if we rewrite these terms that come after the step functions, instead of this t minus 2 expression, I want to rewrite it as something involving t minus 1, since that's where the unit function had its change in definition. So an easy way to do this here, well, I could think of this as t minus 1 minus 1 to get my t minus 2. And then similarly for the u2 term, I have u2 times, well, I want this to be something involving t minus 2. So the t minus 1, well, I can just rewrite that as t minus 2 plus 1. Or if I distribute these u functions, I have u1 times t minus 1 minus u1 plus u2 times t minus 2 plus u2. And so for my Laplace transform, capital F of s, well, I want to take the transform term by term. So for the first part, I have u1 times t minus 1. So by this new theorem, I'm going to have e to the negative 1s times the Laplace transform of the function that was being shifted. So t minus 1 is just t, shifted 1 unit to the right, minus the transform of u1, which is e to the negative s over s, plus the transform of u2 times t minus 2, which would be e to the negative 2s times the Laplace transform of t, plus e to the negative 2s over s. Or using my Laplace table to find the Laplace transform of t, we would have 1 factorial, or 1 over s to the 1 plus 1, minus e to the negative s over s, plus e to the negative 2s times 1 over s squared, plus e to the negative 2s over s. So here we see some examples where we're finding the Laplace transform of some function, which is piecewise defined, by making use of this new theorem. And what's a little tricky is we have to think of this function that comes after the exponential as some function which has been translated the same number of units to the right. So now let's consider some examples working in the opposite direction in terms of an inverse transform. Here we are asked to find the inverse Laplace transform of each function. We've got a few parts. In part A, f of s is 2e to the negative 3s over s squared. And when I look at this one, something that jumps out right away is this e term, e to the negative 3s. So when that term appears, I want to make use of property 13 from my Laplace table, which is theorem 6.3.1. So let me think about pulling this exponential out in front of some function. So I have here 2 times that e to the negative 3s, and then I'm multiplying by 1 over s squared. So I need to know what is the inverse transform of this function. 1 over s squared. So taking the inverse transform, a little scratch work to the side here, of 1 over s squared, that would just be t to the first power, using our table of transforms. So by property number 13 from my Laplace table, the inverse transform, f of t, that is the inverse transform of 2e to the negative 3s times 1 over s squared, is given by, well, I have the constant 2, and because of the e to the negative 3s, my inverse transform is going to have a unit function at time 3, and then I multiply by the inverse transform of whatever came after that exponential. Inverse transform of 1 over s squared was t, but shifted or translated 3 units to the right. So let's look at another one. In part B, I have f of s is e to the negative s over s squared plus 4. And right away, as with part A, this exponential term sort of jumps out at us. We know we're going to try to use our new theorem. And to use it, let's think about rewriting this as an exponential e to the negative s times some function, 1 over s squared plus 4. And then I need to find the inverse transform of whatever comes after that exponential. Here I have 1 over s squared plus 4, which I can rewrite as 2 over s squared plus 4 times a factor of 1/2. And now the inverse transform of this expression, 2 over s squared plus 4, from our Laplace table is sine of 2t. So by using my new theorem, when I'm taking this inverse transform, I'm going to have half the inverse transform of e to the negative s times 2 over s squared plus 4. So I have my 1/2, and because of the exponential out in front, e to the negative s, my inverse transform is going to involve a unit function at time 1. And then I multiply on the end by the inverse transform of whatever came after my exponential, which was sine of 2t, but shifted 1 unit to the right. So I replace t by t minus 1. And this gives me 1/2 of u1 times sine of 2t minus 2. Or let's look at this last part. Part C, we have f of s is e to the negative 2s over s squared plus s minus 2. And again, what jumps out at me is this exponential term. So as we did in the first two parts, let's think about pulling this exponential out in front of some function, which would be 1 over s squared plus s minus 2. And then I need to be able to find the inverse transform of whatever comes after that exponential. So here I have a quadratic denominator which can be factored down to linear terms. S plus 2 times s minus 1. And here, since my denominator is now a product of these linear terms, well, I know I need to use partial fractions to rewrite that product as a linear combination of terms. So using partial fractions, I could rewrite this as e to the negative 2s times 1/3 of 1 over s minus 1 minus 1/3 of 1 over s plus 2. Or if I factor out a 1/3 from each term, I have e to the negative 2s over 3 times this difference. And now the inverse transform of this expression is given by e to the t minus e to the negative 2t. So when I'm finding the inverse transform of this capital F of s function, I have a constant 1/3. Because of the e to the negative 2s, my inverse transform will involve a unit function at time 2. And then I multiply by the inverse transform of whatever came after this exponential, but shifted 2 units to the right. So instead of e to the t, I have e to the t minus 2 minus e to the negative 2 times t minus 2. So we see how to find the inverse transform of these functions that involve an exponential of the form e to the negative cs in front of our function. Now, in the last part of this section, we'll look at one last result involving a Laplace transform or inverse transform of a function which has been shifted. This is theorem 6.3.2 from your text, which says if the Laplace transform of a function, little f of t, which we call capital F of s, exists for some values of s, and if c is a constant, then the transform of e to the ct times that function is equal to the Laplace transform of the function f translated c units to the right. Or thinking about this conversely in terms of an inverse transform, if the inverse transform of capital F of s is f of t, then the inverse transform of a function capital F, which has been shifted or translated c units to the right, is e to the ct times the inverse transform of the function capital F. So let's look at a proof of this result. We need to find the Laplace transform of e to the ct times a function f of t, which by definition is the integral from 0 to infinity of e to the negative st times the function that was being shifted, or the function that we're taking the transform of. And so here I can combine these two exponential terms using properties of exponents by adding their exponents. So I can rewrite this as e raised to the negative s minus c all times t, f of t dt. And now notice that this integral is the exact definition of the Laplace transform of f, but with s replaced by s minus c. So we have the Laplace transform of little f, which we call capital F, but with s replaced by s minus c. And this is what we wanted to prove. So let's look at one last example making use of this result. Here we are asked to find the inverse Laplace transform of this function. And when I look at this denominator for capital F of s, I see that it involves an irreducible quadratic, which can't be factored down to linear terms, but it's also not a sum or difference of squares. So as we've seen in our earlier sections, this suggests that we should try completing the square. For that quadratic denominator. So our f of s expression can be written as 1 over, I would have s minus 3 quantity squared, and then I would have to add 4 on the end to keep my constant 13 in the denominator. Or I could think about this as, if I want to force my numerator to be 2, I have 1/2 of 2 over s minus 3 squared plus 4. And now this expression that comes after that factor of 1/2, well, I can think about this as a function g of s, but where s was replaced by this factor s minus 3. So let's think of this. F of s is given by g of s minus 3, where g of s would be the function 1/2 of 2 over s squared plus 4. And I know how to find the inverse transform of this expression. My inverse transform would be 1/2 sine of 2t. So my theorem 6.3.2 says, well, to get the inverse transform of capital F of s, which was just g, shifted 3 units to the right, I could take an exponential e to the 3t times the inverse transform of the function g, which gives me 1/2 of sine 2t, or if I bring the 1/2 out in front, 1/2 e to the 3t sine 2t.